In this video, we're going to go over gluconeogenesis. Gluconeogenesis is the synthesis of glucose from non-carbohydrate precursors. This happens in your liver and your kidney, and you go through this when you don't eat glucose and you have no glucose or glycogen left in your liver. And certain parts of your body, like your brain, need glucose, so you need to construct glucose. You'll make glucose from certain precursors like lactate, pyruvate, citric acid cycle intermediates, and most amino acids, not including leucine or lysine. And really, all of these things need to be converted into a 4-carbon oxaloacetate, which itself is a cyclic acid intermediate. Note, we cannot use fat to make glucose. And there are different ways you can do gluconeogenesis based on where you enter the pathway. We're just going to consider pyruvate to glucose for this. So here we have our glycolysis and our gluconeogenesis pathways. Hopefully the glycolysis pathway is familiar to you at this point. And if you remember, we have 3 enzymes that are control points for us that have large negative delta Gs. That would be hexokinase, phosphofructokinase, and pyruvate kinase. Since these have large negative delta Gs, these are irreversible, and we need some other enzyme to replace them for gluconeogenesis to do the reverse reaction. So our first step from going from pyruvate to glucose is to convert pyruvate to phosphoenolpyruvate. And since going from PEP to pyruvate, you make an ATP, you need to put in a lot of energy to go from pyruvate back to PEP. So you require energy input. And this happens in 2 general steps. One, pyruvate carboxylase will catalyze the ATP-driven formation of oxaloacetate from pyruvate. So you use HCO3- ATP, go from pyruvate to oxaloacetate. Then, once you're in oxaloacetate, PEP carboxykinase, PEPCK, converts oxaloacetate to PEP in a reaction that uses GTP as your phosphorus group donor. So you can see we use 1 ATP and 1 GTP going backwards, or in this case going forward for gluconeogenesis. So let's take a look at this mechanism then. So pyruvate carboxylase, tetrameric protein, and it has a biotin prosthetic group. Each of the tetramerics, so you have 4 subunits. Each of the subunit has a biotin attached to it. And biotin is going to be your carrier of carbon dioxide. And this biotin is bound to lysine on your enzyme. And this means that biotin is flexible. Lysine's long, and so you have this 14 angstrom flexible arm that's going to be swinging back and forth during this mechanism. And so there are 2 phases for this. Phase 1, you take your ATP and you cleave ATP to make ADP, and ADP goes off. And you attach 1 phosphate to CO3-. You get carboxyphosphate. This carboxyphosphate is extremely high energy, and so you're going to use the energy of chopping off a phosphate group to attach carbon dioxide to this biotin enzyme. And you'll get carboxybiotinyl enzyme. So you have your CO2 combined to your biotin. Next is the phase 2. So that was all phase 1. Phase 2. You take your CO2 and you're going to convert and you're going to give it to pyruvate. So the first step is that CO2 will dissociate from biotin. And then you have pyruvate, which will give a hydrogen to biotin, and you'll form a carbon-carbon double bond. This carbon-carbon double bond will then attack the carbon dioxide to get oxaloacetate right here. So 2 different phases. Biotin is involved in each of these phases. Now for this enzyme, each phase is actually on a different part of the enzyme. So what biotin is doing is that it's swinging from part to part. So if you can imagine, if you picture like a protein in your mind, there are 2 sections of this protein. each section, so one section does phase 1, and separated by some distance, another section does phase 2. In the middle of these two sections, you have your biotin linker, which is like a spring that's just going from section to section doing the chemistry. So in phase 1, you're picking up carbon dioxide. Phase 2, in a different section, you're giving this carbon dioxide to pyruvate. Now, the PEP-CK mechanism, super simple. Here we're using GTP. So once you made oxaloacetate, you're going to get rid of your carbon dioxide by taking one phosphate from this GTP. Now you've made phosphoenolpyruvate, and you have CO2 that needs to be carried out by the blood. That's it for this video. I will see you in the next one.